So, chapter 10. Right, so we're now starting on proteins. These are the workers of the cell. Most of the thing you consider work, you doing stuff, is protein stuff. Now, this is kind of the first chapter where we really start deep diving into biology and biochemistry sort of stuff. Okay? We've kind of went here and there with biology and biology related chemistry. But we're going to deep dive into it now. So proteins, these are going to be polymers. Poly means many, meros means part, and so they're composed of many repeating parts. Okay? And these repeating parts are going to be called amino acids. In case you're wondering, the individual amino acids in this polymer terminology will be called monomers. Okay? So there's actually 20 different commonly occurring amino acids. There are actually other amino acids on top of that, but not commonly occurring. Okay. Now, these can contain, for proteins, as few as 50. They can contain as many as thousands of amino acids, tens of thousands. These things can get very, very large. Okay. In fact, technically, there is not a cutoff. Theoretically, you know the people with like the super long nails and you have that sort of stuff, they're technically building out continuous polymers. Okay? So like you could have like hair that you continue growing out and just wrap it into like a dowel or something. So you could make a very, very large and break the record or whatever. But, usually tens of thousands is where they would have the normal sort of cutoff. Thousands is a pretty big protein. Now, ordering the amino acids in a protein is going to determine its structure and biological function. There's sort of two parts to a protein. There's the order of the amino acids, and then how exactly they folded together. Okay? Now, when you look at a pair of scissors, clip, 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 if it doesn't look like scissors, are they scissors? Would this be a scissor? No. That's not a scissor, is it? This? No. This? No, that doesn't make any sense, does it? Why does that not make sense? Because the shape is the function, right? And so there are proteins that actually look like scissors, and guess what their function is? They cut stuff. Yeah. So there are actually, the shape of a protein is its function. Function depends on shape, right? These things are directly interrelated. You can't have one without the other. Okay? Now, proteins, these can transport oxygen in the blood. They can serve as the main components of skin and muscle. They can defend our bodies against infection. Direct cellular chemistry as enzymes. Control metabolism as hormones. Not that they're the only things that can do any of this, but they are the primary source of all these functions. And many, many more. Basically, if you think of you doing stuff, it's probably a protein. Okay? There's a few things that are not, but probably a protein. Now, amino, this is going to indicate your protonated amine on the amino acid. Your acid is actually going to be a carboxylate, which is the conjugate base of the carboxylic acid. And so that's where the name comes from, right? It has an amino at one end and an acid at the other. Okay? Now, the other features of amino acid are going to be, right here we have the protonated amine. We see that okay? Then we have the carboxylic acid right here, which has actually lost its proton. And so it's a carboxylate ion. Notice we have an acid portion, we have a base portion, don't we? And so whenever we have amino acids in a solution, well, they're always going to lose their H plus to the base part. So they'll always have the conjugate acid, conjugate base form at your neutral pHs. Okay? Now, the carbon here, this is called the alpha carbon. It's the next carbon over between the two different functional groups. And so that's referred to as alpha, and it's called alpha carbon then. Okay? Up here, this is the side chain. You may have heard of different proteins like alanine, glycine, tyrosine, those sort of things. Well, they all are different by the side chain. Okay? This is why we have 20 different ones. It's because they're different at the side chain. They're all the exact same here, essentially. Now, we have one more thing. That's a hydrogen. Nobody cares about hydrogen, so we ignore it. Okay? But, see, it's even in black. It's like, it just give normal text coloring to it. I don't even label it special. It's neglected hydrogens. Now, what do you notice about this carbon? Is there something special about that carbon? How many things are around that carbon? 4. There's 4 different things around that carbon. Is there something special when there's 4 different things around that carbon? That's a chiral carbon, isn't it? Oh my goodness, it's like everything I've been teaching you, I taught you for a reason, so we could use it here in these more advanced topics, and you could actually understand some of this. Dr. Claus, it's like you expect me to remember things. Terrible, I tell you, terrible. Okay, and so this is a chiral carbon, of course. It being a chiral carbon, there are 2 enantiomers, aren't there? Okay. Now, the enantiomers for amino acids are going to follow the exact same pattern as sugars, because biochemists don't really understand enantiomers. I don't know what to tell you. Like, they basically set up a way of identifying enantiomers that has nothing to do with the actual structures themselves, and then labeled everything that way. So that's biochemists. What to tell you there other than that. So what they do is they take the carboxylic acid portion, that goes straight up in a Fischer projection. The R group goes straight down, and then they have the amine and the hydrogen going left and right. So remember, Fischer projections, this part here is going away from you. Okay? This part across is coming out towards you. All right? Now, if it's on the left side, we call that an L amino acid. So it'll be the L version of alanine. Okay? L version of glycine. If the amine here is on the right side, that's going to be D. And so that'd be the D amino acid. Does this have any other meaning? No, not at all. Okay? There is no other correspondence to D and L here other than left side for this, right side for that one. And that's it. There is absolutely no other difference. Now, the L amino acids are the building blocks of proteins. They're the ones you see everywhere, almost all the time. So the D amino acids, on the other hand, do occur in nature, but very rarely do they get incorporated into proteins. Okay? So if you were trying to build up and bulk up because you're like exercising, you're going to do some sort of sports event, if you eat the D amino acids, you're going to have very little effect. Okay? If you eat the L amino acids, you're going to use basically almost 100% of those. Okay? You'll use a large portion of those. All right? Now, the side chains, or R groups, gives each amino acids its unique identity and characteristics. There's 20 amino acids that are found in most proteins. 9 families of organic compounds are represented. We have the alkanes. Those would be those hydrocarbons. Remember the C carbon-carbon single bonds with hydrogens across everything, right? Aromatics. Anybody remember aromatics? 6-membered ring with the alternating double bonds, right? Okay. Sulfides. These are going to have a bond to a sulfur and another bond. Okay. Alcohols. These are going to be OHs, aren't they? We have phenols. That's the aromatic with an OH on it, right? And then we have thiols. These are going to be SHs, like an alcohol, but with sulfur. Okay. And then we have amides. These are going to be the N next to a carbon-oxygen double bond. And then we have the carboxylates. Those are going to be the D-protonate, bless you, carboxylic acid. And the protonated amines, of course, which are the amines that got protein. Now, the properties of these different functional groups are going to allow these to be classified under different classifications. The first level of classification is going to be polar and nonpolar. Okay. For example, the aromatics and hydrocarbons, those are going to be nonpolar, aren't they? If we were to look at things like the alcohols and the thiols and the amides, these things are going to end up being polar. Notice these charged ones as well are going to be polar as well, aren't they? Okay. Okay, so under that classification of polar, we actually have another classification we can use. So at physiological pH, are they going to be neutral, acidic, or basic? Okay. So we have the ones that will be neutral, acidic, or basic. All right, so let's look at these classifications for these R groups. The purple parts here, those are the R groups. See that? Okay. And so this is glycine right here. It has another hydrogen. This is the only one that's achiral, that does not have chirality, by the way. Because it has two hydrogens on it, can't be chiral. Okay. This is alanine here. This has a CH3, that's a hydrocarbon, isn't it? Yeah. And then we have over here valine, and see the little V shape? Valine. I know. That's an isopropyl group, isn't it? And then over here we have another hydrocarbon. This is leucine. See, again, it has an iso group right here, which is the these three right here. Now, one of the things I need to warn you about here, remember how isomers? So leucine has a little V shape here. Isoleucine, we've moved it to what's called the sec position. Okay? And that's called isoleucine because it's an isomer of leucine, isn't it? This right here is going to be phenylalanine. So we have a phenyl group right here. That's an aromatic group. This one, by the way, is just directly the organic naming. So it's alanine, right? With a phenyl. You gotta love it when they actually name things something that makes sense. Mm-hmm. Yeah. Methionine, by the way, is also it is the organic naming. It's another one. And so this right here would be thio, meth as in methyl, right? Mm-hmm. So methionine. And that's the sulfide right there. This right here is going to be the hydrocarbon. This is proline, pro as in propyl, right? 3 carbons. And this one's kind of easiest one to remember if you ever have to memorize them, because it looks like a P. So, yeah. This one's trippy. It's tryptophan. Interestingly enough, it actually looks, this side chain is very similar to what you'd find in like actual psychedelics. So it's actually, it also looks a little bit like a base that you find in DNA. Yeah. So it's not. They're a little bit different. But that's tryptophan right there. Primary alcohol is going to be serine. Notice this is the start of the neutral polar amino acids. And so when you drink too much alcohol, you become serine. Threonine actually is a really great name for this because it has 1, 2, 3 different groups off that carbon, doesn't it? And so it is threonine. Tyrosine looks a bit like tire. That's the phenyl group, by the way. So that's phenol right there. And tyrosine is the name of the amino acid. This is a thiol, by the way. This is cysteine. Anybody that has curly hair, you have more of these in your hair. Okay? If you try to curl your hair, what you're doing is you're actually trying to activate these thiol groups. Okay? And so the thiols are what makes that curling. They do what's called disulfide linkages. If you straighten your hair, you're actually breaking these disulfide linkages. That's why it smells weird like that. Okay. And so this is asparagine right here. This is the amide. It looks a little bit like asparagus. And funny enough, the smell to asparagus is actually due to amines. So that kind of works. This right here is another amide, but has 2 carbons down here. And so that's glutamine right there. Aspartate has a carboxylic acid. And this is going to, again, be the 1 carbon one here. Notice it has carboxylic acid on the side chain. These ones right here, the polar amino acids. These ones up here, the amides, are neutral. This one down here, well, these ones are acidic because they have acids on the side chain, don't they? And this will be carboxylate again, and it has 2 carbons, and so that's glutamate right there. These ones right here are going to be, again, polar amino acids, but these ones are going to be the basic ones. And so, basic as in being a base. Notice this is protonated now because it was a base, wasn't it? And so this is histidine. It has the 2 amines in it, okay, which is what gives it that activity that you know of and you probably have heard of. Lysine is going to have the nitrogen at the end of this long chain here. That's lysine. And this is arginine right here. It's going to have the 2. This is actually called an imide, by the way, this double bond right here. It's kind of a unique one. But that one right there is arginine. So the 10 amino acids that are designated with the asterisk in the table, these are called the essential amino acids. They are essential because they cannot be synthesized in the human body. You have to obtain them through your diet. And so they're the ones you cannot just make yourself if you have the base materials. Okay? 2 of these amino acids, arginine and histidine, are actually essential in the diets of children, but not adults. Once you have enough as a child, you no longer typically are considered needing these. Okay? Proteins that contain all the essential amino acids are known as complete proteins. These would include things like soybeans, eggs, milk, fish, poultry, and meats. It's really funny to me that some of these have been put on lists in the last 20 years as being unhealthy for you. I think anything that has a complete protein can't be that unhealthy for you, but eating in moderation is a good idea. So some proteins from plant sources are actually incomplete proteins. This is because they lack 1 or more of the essential amino acids, of course, and so they would be incomplete because they lack those amino acids. A complete protein meal can be obtained by combining certain foods. And so even if you use an incomplete protein, what a lot of cultures do is they actually have recipes that would combine incomplete proteins to give you a complete protein source. Okay? And so some of the classifications for amino acids, again, the 2 broad classifications that should be at the top of your mind are the nonpolar versus the polar. Okay? Is it nonpolar or is it polar for the side chain? With a few exceptions, the side chain of nonpolar amino acids are going to be composed entirely of carbon and hydrogen, and they're typically going to be hydrophobic. That's what nonpolar ends up being, hydrophobic, right? They're very rarely going to have any hydrophilic properties at all, and so they are hydrophobic. Tryptophan is going to contain 1 nitrogen atom. This contributes very little to its polarity. And so tryptophan is considered nonpolar overall, even though it has the 1 nitrogen. Remember we were talking about things being nonpolar because they just have so much more London dispersion forces versus being the polar part. Methionine actually contains a sulfur atom. It's nonpolar because the carbon-sulfur bonds are nonpolar in general. And so it just doesn't have enough polarity to actually be very meaningful. The polar amino acids are going to be divided into 3 groups. We'll have the neutral, acidic, and basic subclassifications. So the polar amino acid side chains will have certain functional groups. These are going to create uneven electrons in your side chain. All of the polar amino acids, except for cysteine, which has an SH group, can form hydrogen bonds with water. SH does not actually have a hydrogen bond donor, right? Because it's not one of those 3 for hydrogen bonding. Nitrogen, oxygen, and chlorine. Now, this will make them hydrophilic for all of those, and this will cut off. The polar acid and polar basic amino acids have charged side chains at physiological pH, and so they'll have ion dipole interactions in water. You all have a great day. I'll see you next time. You take care now.